Welcome to the Farnborough branch of the Royal Aeronautical Society for tonight's lecture on aircraft electrifications by Dr. Temoc Rodriguez. Before we get started, a couple of notices. First is a plug for our next lecture on the 11th of May, which will be on the Rolls-Royce UltraFan programme. And then the following one on the 15th of June, which will be on the ethics and legalities of UAV operations. Hopefully you can join us to those. The links will be available and sent out as usual. Tonight we have enabled the captions, so if you do have difficulty with the sound or hard of hearing, you can enable that by going to the settings menu, which is the little cog I think you'll find in your top right display, and if you then go down about 2/3 of the way, you can enable that and you'll get a pretty good translation of what we're saying. So please feel free to use that if you wish. The other thing to remind you, we'll ask questions at the end of the presentation. However, if you could type them in to the questions field as we go along, that will enable us to sort some of them out and avoid any duplications. Other than that, welcome to Dr. Temoc Rodriguez. He, better get this right now. He completed his PhD in electrical engineering at Cambridge. He's worked on numerous industries, not just aerospace. He's worked in automobile, oil and gas, and has worked for, currently works for Ricardo, previously with Ultra Electronics, where he led teams developing engineering solutions for Airbus, Boeing, Pratt & Whitney, Gulfstream, Embraer and Mitsubishi. So a very broad set of experience there. So I'd like to welcome Temoc to take the stage, figuratively speaking, and provide us his presentation. Thank you very much.
Thank you, Paul, and thank you to the RAeS and the IET for inviting me tonight and allowing me to present this set of slides on aircraft electrification. This is a piece of work that I've been collating for a couple of years, as I've seen the industry almost turn upside down, partly as a result of the pandemic a year ago. Before the pandemic hit, we were on an increasing trend on airline operations and number of aircraft being manufactured by the big players like Airbus and Boeing. And unfortunately, the pandemic turned that on its head, and we saw pretty much most airplanes grounded over the world, and airlines consolidating and shrinking in size and parking all aircraft or inefficient aircraft and making room for the more recent aircraft and more efficient aircraft. But another thing that happened is that whilst all these well-established industry companies were trying to mitigate their losses, we saw the focus shift towards urban air mobility and electric aircraft and hybrid aircraft. And it has been a great opportunity for those companies to take the spotlight and showcase what they've been doing and take their technology to the next level and raise more venture capital and start the processes to get their aircraft certified. So this presentation tonight, really, it comes at a good time to give you an overview of what the situation is with all these companies around various countries. And what is the road to get those aircraft certified and providing services to people like you and me. So hopefully you will enjoy that. So let's get cracking. A little bit of introduction about Ricardo. Ricardo is a big company. We have offices all over the world, mostly in the US and the UK. And we cater to a number of industries, traditionally an automotive company, but we have now expanded to a number of sectors from rail and energy and now into aerospace. And we work in a number of areas around life cycles and developments, from strategic consulting to R&D, and all the way through detailed design, development, and product introduction, and manufacture as well. And more recently, as we've seen this aerospace sector grow, we've been translating the expertise that we have in automotive electric powertrains into aerospace powertrains. This is a schematic view of the areas where we operate. Essentially anything to do with the electric powertrain we are involved in. And we have a number of ongoing projects at the moment that deal with some component along this powertrain, from hydrogen fuel cell power sources to distribution, power conversion, motor drives, electric machine design, transmissions, gearboxes. Thermal management is very important, and I'll explain why that is in a few slides later. And the machining and manufacturing of precision parts that go into mechanisms that move the various flaps and ailerons and so on. Now, why has this need arisen, and why now? I mean, we saw the car industry doing it, in the mid-noughties, so that they could launch vehicles in the early 2010s with, the Nissan Leaf and the likes. So what has taken a little bit longer for the aerospace industry to get on board the electrification bandwagon? And part of the reason is that the components were not there at the time, but they are there now. So things that are happening is, as you will be well aware, that there's government policy about limiting the emissions that have an impact on global warming, and there's more localized government policies around how we transport people. Some countries have gone as far as banning short flights if there is an electrified train route, and as a result, some of the airline operations in those countries are quickly starting to invest in electric air mobility solutions. We know that aviation emissions account for 3% of CO2, but more like 5% of combined global warming effects once you include the NOx emissions and the contrails and so on. And of course, because they are at a higher altitude, they may have a more severe effect on global warming than emissions at ground level. Now, the other thing that has happened is the evolution in lithium-ion battery technologies. So since lithium-ion cells became mainstream in the early noughties, we've seen a doubling in capacity for the same volume, and that means you just pack more energy in a small volume. Now, by the 2010s, that was sufficient for cars to, pack, 500 kilogram battery pack at the bottom of the car chassis and get it going. Now, of course, that is not sufficient for an aeroplane, because aeroplane has to take off the ground. So we've seen more improvements in those battery cells since 2010, and they have reached a point where now it's feasible to transport that heavy battery pack in an electric aircraft and still have routes that make sense, that have a business case around them, and therefore have made it feasible to develop these aircraft and put them into operation. Now, the other thing that has happened is the motor technology that goes with it and the power electronics to drive it. We've seen a very sharp increase in power density, from those industrial motors that are the workhorse of our industries, bulky machines but reliable. When the car industry started electrifying, we saw a big drive to try to pack more power into smaller volumes so that they could fit in either as a hybrid or a standalone electric vehicle. Now, initial aeroplane prototypes used those motors, and those were sufficient for demonstrator flight. But what has happened since is that motor design has taken a tangent away from automotive designs, and now we are packing more and more power into a very small volume and weight. So we are talking double the amount of power density compared to a car motor. Now, of course, the car industry is now going in a different course because they are more concerned about the cost and the security of supply that goes into those motors, whereas the aerospace industry is concerned more about taking off the ground, right? So we need light equipment. We need to pack a lot of power in a small volume in a small weight. And all of those factors have now coalesced into the situation today, and has enabled the creation of these electric aircraft and supported the business case for electric aircraft operations. So what is happening? Roughly speaking, initiatives can be broken down by range. We have what we call the urban air mobility, UAM, which is essentially transporting people within the bounds of a city or a dense populated area. You can think London with a number of hubs or vertiports, as they call them. So you can imagine, for example, a hub at London Heathrow, and one at central London, right? And then you can get an urban air mobility air taxi. Essentially, takes you from Heathrow to central London in about 5 or 7 minutes. Right? Compare that to a train that will take you 30 minutes or so. So that is the general concept of urban air mobility. Now, sometimes they call this advanced air mobility because this type of aircraft, there's some type of aircraft that can change from vertical lift into horizontal flight, and then they use wing shape and aerofoils to create lift and lower the power demand on the battery and the motors. And those are able to travel further distance, and they can cover distances between cities. They call them intercity aircraft. And then we have the regional aircraft that cover roughly a range of 300 miles. So you can think of London, Dublin, Edinburgh, Paris, Amsterdam, right? That sort of range. It's entirely feasible to do that with fully electric aircraft. And that is the boundary roughly at which hybrid aircraft also start to operate. Obviously, what hybrid gives you is that additional energy density that comes from a fuel, and that fuel could be jet fuel like we currently use, or it could be hydrogen. There's a big hydrogen hype at the moment, and it is like a second or third or fourth wave of the hydrogen economy, because it started back in the 70s. I think it was the first wave, and I remember a hydrogen economy wave early in the noughties as well, and now this is yet another one, right? And hopefully this one will last. I think our industries are mature. Our will to change our attitude toward the environment and towards global warming has changed. So hopefully this time it will endure. And I'll talk a little bit about those hybrid aircraft. So the story started with a bunch of demonstrators, smaller aircraft, which are easier to lift off the ground, and there's some specific purpose demonstrators to try to validate some of the technologies. So, for example, we have the NASA X-57, which is still ongoing in the United States, and what they're investigating is the effects of having distributed propulsion, along the wings. Obviously, it's a conventional takeoff aircraft in this case, but they are experimenting with those wing shapes and the effects of having these distributed propellers along the wing. And the general idea is also to test various fuselage shapes to try to optimize the aerodynamics of the aeroplane to make it specific for electric propulsion. And then they have a number of cruising propellers and lift propellers. So the little ones are only on during a takeoff. Once you are at a certain altitude, you only use the outer cruising motors. Alpha Electro here in Europe, they developed this trainer. It's like a trainer aircraft for the pilot and one more passenger. It's very small. You can see there with just one motor, and that is fully certified now. So it was probably the first electric aircraft to be certified for passengers, for one passenger. Then we have here in Britain the Rolls-Royce Excel program, a very, very sexy program, right? And you can see from the design they came up with, it looks almost like that in real life or in photographs of the real thing. But the idea of this demonstrator is to explore packing a lot of energy into a very small space, and then coming up with redundant architectures for battery management and propulsion. So at the front there you see the propeller, but there are actually 3 motors stacked together, giving it a lot of power. And their ultimate goal is to produce the fastest electric aircraft ever made. But really the intention behind it is to prove how much energy and power you can pack in a very small space. And bottom right there you can see the first of the Airbus electric demonstrators. That is probably 8 years old or so. And he flew across the channel, and he demonstrated that they can do electric flight. So in a nutshell, all these demonstrators show that yes, electric flight is feasible. They can build in high integrity and redundancy into the systems to make them safe. And now it's all a matter of building a business case around the routes that they can cover, right? Because being heavier, being and maybe smaller, they can only go so far, and they need to see how that integrates with the rest of the transport network and start complementing areas where they can operate and they can make business. So, and that is what leads us to the actual commercial developments. So they're broken into various types. The ones that you see here transition between vertical hover and horizontal flight. And they are shaped in a way that they can take advantage of aerodynamic lift as they start accelerating horizontally. And these two that I have in big pictures there are probably the 2 front runners in this race. And that's because they have a lot of investment poured into the coffers. Both of them have received both of them have been floated. Essentially, they've gone through something called the Special Purpose Acquisition Company investment, and then floated in the stock market. And that has poured loads and loads of millions into their development programs. So, I mean, roughly speaking, to get an aircraft of this type certified and operational costs about $1 billion. So that is not a small sum, right? It is not money that will come from the UK government to demonstrate aspects of the technology. So that, that's how it starts. But to really get an aircraft into commercial operation takes a lot of money. It's not just proving that you can get an aircraft off the ground. It is proving that you can do so safely and repeatedly, and then building the infrastructure that you need around it. So these guys are working with city governments, with large transportation organizations to try to build those routes and build the connections between different transport options. And here in the UK, you may have heard of vertical aerospace. They are recently new into this market. They have a concept aircraft for passengers that now they are starting to develop. And more recently in the news, you will have seen that they have partnered with Rolls-Royce to develop the powertrain and the propulsion system. So that's good news for VA, and hopefully we'll see it through. And Kitty Hawk is another one that has a long history in the US. has some investment, but not at the level of these other two guys. Now these ones are really the urban air mobility concepts, the air taxis. Volocopter, based in Germany, is already certified, and it can carry only 2 passengers, so fairly small aircraft. And they have established some operations in Singapore as well, where they will launch first, and also in Germany. And Airbus have invested in all sorts of concepts, but this is their urban air mobility concept, the Airbus City. Again, they are partnering with Rolls-Royce to develop the propulsion system there. And other players there you see at the bottom of the screen are Embraer and Hyundai. More recently, Hyundai has been in the news because they are collaborating with the creation of a vertiport in Coventry. So hopefully that will go ahead nicely. So beyond the bounds of city travel, we have these regional aircraft. Now, Aviation is an Israeli company, and they have some operations in the US as well. And they built a number of these demonstrators, the Alice, and they've showcased it at air shows like Paris, and I think they came to Farnborough as well. So this is a larger aircraft. It can carry 9 passengers, and it can go a fair distance, 540 nautical miles. It also carries a very heavy and large battery, which allows them to go that far. But now you can see that by having a clean sheet design in terms of the structure and the propulsion system, all the internal systems, they've been able to design an airplane that can service those regional routes. It is the only of its kind. The other ones on this page are conversions of the Havillands or Cessnas, Britten-Norman, essentially by stripping out the fuel tanks and the engines and fitting in electric propulsion systems. So that one there on the top right is the Harbour Air in Vancouver, where they stripped out the engine of the Havilland. This a Beaver version, and they fitted a Magnix motor. Magnix, you will see it later, is one of the new players in electric machine designs for aeroplanes. They specifically target aerospace. They have built-in redundancy and thermal systems to pack a lot of power in a very small volume. And that same motor is also was fitted to the Cessna E-Caravan, which again is just a retrofit from the Caravan. They stripped out the fuel system and fitted the electrical system, and then carry a lot of batteries inside. And the Britten-Norman, as you will be aware, here in Britain, has received funding from the government to do a conversion as well. Initially, it was going to be all electric, and now they've changed direction. Really, they realized a full electric aircraft was not going to give them the operations that they needed, and now they're going for a hybrid with a hydrogen fuel cell. And at Ricardo, we are helping them with the development of that hydrogen fuel cell. Now, another company, also here in the UK, but also in the US, is Zero Avian with their high fly version. This is like a smaller demonstrator. Their ambition is much larger, to develop a larger passenger aircraft. But again, in this case, Zero Avian are targeting aircraft with a hydrogen fuel cell powertrain. And then you have others like Farnborough, also here in Britain, and Zunum Aero in the US, who use conventional fuel or synthetic fuel, perhaps, again in a hybrid electric configuration. Now, once it gets to long haul, there is not many players looking into it, because you know, once you put your numbers in a spreadsheet, you realize that, well, battery is not going to cut it, and I'll show you some examples of that. So they need you know, a liquid fuel of some sort. It could be synthetic fuel, but it could also be hydrogen, liquid hydrogen. And Airbus are looking into various different concepts of hydrogen powered planes, either to burn it directly in hydrogen gas turbines, generate thrust from that, or having some hybrid parallel series configurations with some electric assistance. And Wright Electric, who pioneered at some point with EasyJet, also wanted to do a hybrid electric, maybe using synthetic fuels. At the moment, they've gone quiet for now. I think they're in the next round of funding, if you like. Right. So let me talk to you about the technology behind these aeroplanes. What makes them unique? What are the challenges? So one of the first things I wanted to understand when I started looking into this is, at what point do hybrid aircraft become necessary based on today's technology of battery cells and motors and so on? And I did some quick calculations on the energy required for small, medium and large aeroplanes to cover a route covering a certain number of passengers. So I have a small route there, London-Paris, 300 miles, flying at a speed of 300 miles per hour, carrying 15 passengers. And that roughly takes about 10 megawatt hours. Then you have medium size aircraft covering a route like London to Milan, 800 miles, now carrying 150 passengers at a speed of 600 miles per hour. And that, you can see now, uses 60 megawatt hours. And you know, the very large aircraft covering long haul routes like London to New York City uses quite a lot of energy. Now, one thing that I've kind of quickly figured out is that, well, none of these could be powered by batteries, because the amount of batteries you need to support that level of energy is quite large, and the weight would be quite big. So essentially, once you go past the 1 megawatt hour, roughly, you can no longer do it in an all-electric configuration with today's battery technology, and you need to start considering hybrid configurations. So hybrid aircraft at a very simplified schematic level would look like that. This is a series hybrid with a gas turbine. I've shown a single gas turbine and electric generator. There could be two, one for each engine. But essentially, the principle is that you burn your fuel, either a synthetic fuel or hydrogen, in your gas turbine, which is coupled to an electric generator that generates electrical power and gets that power into battery banks. And then you have that electrical network feeding into your two electric motors that drive either propellers or ducted fans. And all of these high power transfer is done at fairly high voltage to keep your currents down and your electrical losses down. And the idea behind the series configuration is that you'd be able to maintain that gas turbine running essentially at just one operating point, which is the design point of maximum efficiency of that gas turbine. Now, as you'll know, thermodynamic cycles will limit the efficiency of that gas turbine to, I don't know, something like 40–50%. So a lot of losses will go there from converting the fuel into electric energy. Whereas the electric motors are more efficient in a wider range. You know, they can operate 92 to 96% efficiency over a wider range. So that is the general principle, right? So you operate your gas turbine at one very high efficiency point and let your electric motors run at a wider range at high efficiency. Now, the series configuration can also be done with a fuel cell. So you still have your hydrogen tanks, but now they feed into the fuel cell, which generally operates at a higher efficiency than a gas turbine. You know, you could be hitting your 60% efficiency. And again, you run that at high voltage to keep your losses down, and the rest of the powertrain is the same. In a hybrid configuration, you have your gas turbines directly coupled to your ducted fans, but you have them mechanically coupled to the electric machine. So you either burn the fuel and generate propulsion from there, or you can power it from the electric machine, or you can do both. Yeah, you both can input power into the shaft that drives those fans. Now, the general idea on a hybrid parallel configuration is that you can use your electric machines to get you off the ground at the airport, within city boundaries, where you want to keep your noise down and your pollution levels down, and then you use the energy from your battery banks. You get off the ground, you reach cruising speeds, at which point the engines take over. You start burning fuel, but now you start burning fuel at a higher efficiency level because now you're in cruising speed, and you can use also some of that power via the electric machine to recharge your batteries. So overall, the mission, the whole mission, ground-to-ground profile of emissions is lowered because you maximize the use of electrical energy when you need it the most, and you can keep your gas turbines operating efficiently at cruising speeds. In an all-electric aircraft, well, you don't have any fuel. It's a lot more elegant and simpler as a design, as a system. It's all electric. You don't have to worry about fuel lines, which eliminates, not only the system design of where you route the fuel lines, but you eliminate all the risk associated with those fuel lines, right? And from a safety perspective, all the mitigations that you have to put in place for equipment deployed near fuel lines in an aircraft. So all of that is gone. It's all fully electric. You have battery banks, as many as your redundancy requires and your safety cases, and you power your electric motors. I've shown 2. There could be more than 2. And if it's an air taxi, you'll probably have 6 or 8 or even 12, or like Volocopter, maybe 18. But the fact that it's all electric makes the system design a lot simpler. Right, so just a little bit of thought behind electric versus hydrogen, and whether we should really be looking at electrifying even long-haul aircraft longer term. And this hopefully will give you some perspective of how we use energy. Now let's assume we are going towards an environmentally friendly society, where we don't want to be generating emissions that contribute towards global warming. We get all our energy from renewable energy, like I have there, from solar panels, windmills. It could be wave, it could be tidal, and potentially even nuclear. Why not? Some countries are doing it. And you use that energy to generate your green hydrogen. I'm not going to go into the details of the various colors of hydrogen, but suffice it to say that green hydrogen is hydrogen produced by electrolysis using energy that has come from renewable energy, like solar or windmills, and therefore does not generate any emissions. Now, that electrolysis process is usually about 40% efficient, so you will lose, these percentages are energy lost. So you lose 50 to 60% of energy in that process. Then it'll be transported, maybe pipes, maybe tankers, lorries, and there will be some leakage, in the fueling and extracting of the fuel and so on. 1 to 5% of energy will be lost there. Once you get into your vehicle, in this case, I've shown a fuel cell path right there. again, the fuel cell will lose between 40 and 60% of the energy, and then the electrical conversion to mechanical will lose between 3 and 8%. So on the fuel cell path, hydrogen fuel cell path, from source to propeller, we've lost about 72 to 86% of the energy. So not great. And if we decided to burn it in a gas turbine, then from source to the ducted fan, then again 75 to 85% of the energy is lost. In contrast, in a fully electric aircraft, well, we just transport that energy, we charge it into batteries, the batteries discharge, which will lose between 5 and 10% of the energy. And then we have that electromechanical conversion of up to 8% of the losses, and that gives us a total loss of between 12 and 22% of the energy. So when you step back and look at these numbers, as engineers, we want to minimize energy losses. Losses are bad for multiple reasons, right? But there's economic, there's wear, there's heat dissipation that has to be managed. Losses are not good. So from a systems point of view, if we can have a fully electric vehicle, that makes a lot of sense. Now, I'm not saying this is not required. I think this will be required, and a lot of the effort at the moment is around producing that green hydrogen, but producing it at points where the energy is pretty much free, almost unused. You don't want to be robbing energy from renewable sources just for another part of the country to start burning gas or coal, right? So that green hydrogen needs to be produced at peak powers, at peak renewable energy levels, where it would otherwise be clipped by the operators, if that makes sense. Right, let's carry on. So back to my table of energy requirements for a small, medium, and large, and now I have a couple of columns showing how much weight in jet fuel it would need and what would be the equivalent in batteries with today's technology. So this is based on jet fuel having an energy density of 12 kilowatt hours per kilogram, compared to lithium-ion cells having an energy density of 0.3 kilowatt hours per kilogram. And that's not even considering the pack. That's just this cell. Normally that has to be packaged into some fairly sturdy casings with thermal management and so on, which will bring it well below 0.2. But for the sake of this exercise, let's use that number. And you can immediately see that it doesn't make sense, right? Those weights are incredibly large. And the aircraft will not even move. So we need some disruptive technologies if we want this battery approach to work. So I did a little bit of research on what is happening in battery world. And there's a lot of research groups out there investigating all sorts of chemistries and materials and approaches. And all of them tend to revolve around, or most of them tend to revolve around lithium. Some people looking at sodium and some people looking at aluminium batteries, but most of the efforts are around lithium and various approaches with lithium. So there's some research around the materials that go into the anode. There's research on solid electrolytes, which I will explain in a minute, and there's some research on lithium sulfur. And lithium sulfur promises to give us energy densities of about 0.7 kilowatt hours per kilogram, and even with that energy density, it just doesn't add up. We cannot get this aircraft off the ground with those energy densities. So is there anything else? Well, there is something else. Some people are looking at lithium-air batteries. So this is where it works almost like a fuel cell, where air and specifically the oxygen in the air is fed through to the cathode, and you have the pure lithium metal in the anode. And in those configurations, you can achieve energy densities theoretically between 3.5 and 11 kilowatt hours. Now 11 kilowatt hours is getting very close to jet fuel energy densities. It's very unlikely we'll get to those levels, but let's see what happens if we feed 3.5 kilowatt hour per kilogram into our table. And then now you can see that, you know, those weights start to become more reasonable. Now, as an example, just to ground this, a 787 maximum takeoff weight is 250,000 kilograms, and it can carry a fuel capacity of 161,000 kilograms. Right? Well, a large aircraft with batteries that achieve this energy density are 114,000 kilograms. Right, so it will work if we can get these lithium-air batteries sorted, and that is not an easy feat. So what is the issue with lithium-air batteries? So as I say, you have lithium metal in the anode, and that, when it discharges, releases the electrons that flow through the load, and they recombine with the oxygen and the lithium ions that migrate across the solid state electrolyte to form lithium peroxide. And the oxygen comes from an intake of air, which will have other gases, not just oxygen, which may degrade the cathode material. So that's the general principle. Now, this lithium metal is incredibly reactive, and it could become explosive when in contact with water. Now, most conventional batteries will use a gel electrolyte, some water-based electrolyte. So when you have a water-based electrolyte and a lithium metal anode, no, that's not a good combination. You know, that is not a safe cell. So that's where the solid electrolyte comes in. If we can make that solid, as some researchers are currently looking into, then that junction between the anode and the electrolyte becomes feasible. There's other issues. So far, all the demonstrators have a very short cycle life, maybe 10 charge and discharge cycles, which is not great. The oxidation and reduction rates are fairly slow, which means that the cell cannot provide large amounts of current, like peak current, like you, for example, see in lithium polymer cells. So again, it's a cell specifically made for energy rather than power, and sometimes in some parts of the mission profile you need high power to get you off the ground, for example. So again, just a complication in the configuration of the number of cells that you'll need in parallel to achieve a certain power level. As I said, some presence of other gases in the air mixture can degrade the cathode. And up to date, all the demonstrators have been running at fairly low efficiencies of around 70% compared to 96, 97 of lithium-ion cells. Dendrite formation in the anode can short across the electrolyte, typically in a wet electrolyte or a gel electrolyte. That can easily happen. With a solid state electrolyte, that may be more difficult. Some of the challenges with the packaging of the cells, as I said, an aircraft will require a certain amount of energy to complete a mission and a certain amount of power to get it off the ground. And your battery pack has to be designed to be able to deliver both requirements. These packs are typically designed to operate at around 800 volts, in a range between 600 and 800 volts. But the trend, the wish is that we could operate at higher voltages. Now, higher voltages brings its own challenges in terms of arcing, dielectric insulation thicknesses, and so on. But the advantage would be lower operational currents and lower losses in the system. There's in an aerospace battery pack design, there's some requirements around prevention of fire and smoke when a cell fails. We need to prove by test that when you short a cell and it starts smoking, that can be contained within the pack, not propagate to other cells or beyond the pack containment. We also want to maximize the energy that is available in the pack, that is available to use from the pack. And the issue with this is that cells from the manufacturing line, they naturally, due to tolerances, come at different energy capacities. So they can be matched at production by running charge-discharge cycles. We can select cells that are fairly equally matched, so that when we have our pack level battery charging system, they follow the same charge and discharge profile. Now, over time, they will start to drift based on tolerances and perhaps slightly different hotspot temperatures across the pack. And what would happen is that if a cell has a degraded capacity, so lower capacity than other cells, the battery pack charges. Once that weak cell reaches its terminal voltage, then it will force the charge system to stop. So otherwise it would overvolt and create a hazard. But essentially what that ends up with is a battery pack that has hundreds of cells in series, and all of them but one maybe at 97, 98% when one has reached 100%. And that's not great, right? Because that accumulates over hundreds of cells. So what needs to happen is to have active balancing. And one example would be like, as the cells are charging, the weaker cells that have reached 100% faster than the other ones actively get discharged, so that the voltage drops, whilst the remainder of the cells carry on charging. And once they reach 100%, all of the cells will then reach 100% at the same time. And that gives you your maximum available capacity from that battery pack. And then there's challenges around the heating and cooling. Battery cells like to operate around 20 degrees C, but aircraft get deployed from minus 40 degrees C to plus 70 degrees C once you take into account the heating effects of the aircraft. On a hot tarmac in Dubai, and batteries don't like those temperature swings, so it has to be active heating and cooling of the battery cells. And then there's the usual health and usage monitoring, and of course crash tolerance. And now in this diagram I've shown redundancy of the battery packs. That can be implemented in a number of ways, depending on the propulsion architecture. So you can either have battery strings that are able to decouple from a bus, electrical bus, and able to switch to another bus when a fault occurs, for example. So you isolate the fault, you reroute power from another string to maintain system availability. Now, when it comes to charging, the same challenges that we've seen in the automotive industry map across the aerospace industry. So to have fast turnarounds of aircraft, we could have battery swaps. So aircraft lands, the whole pack comes out, a new fully charged pack goes in, and is able to charge within to fly within 5 minutes. There could be onboard charging, for those general aviation small aircraft that fly to land strips in remote places. You may want to charge that using your standard electricity outlet. So there may be an onboard slow charger. Just land, charge it overnight, and you can fly the following day. Or they could be high power fast chargers in vertiports and hubs, similar to what we've seen in the car industry. So several hundreds of kilowatts being poured into your battery pack for about 15 minutes. That allows the pack to charge to about 80%. Good. Right, let's talk about electric propulsion. So, as I said at the beginning, most of the initial efforts exploited the developments in the car industry, as motors became more power dense. But they have diverted since, and now we are seeing aircraft exceeding power densities of 5 kilowatts per kilogram, compared to about 2 or 3 for cars. 4 kilowatts is the highest I've seen in a car. There is also the need in aerospace to have redundancy. So most of these aircraft motors have dual coils, and I'll explain how that works later on. And they are optimized to drive a propeller or a fan, so generally the speed range is fairly tight compared to the wider range that you see in a car. And of course, we want to be operating at very high efficiency to keep those losses down. Now, these are some examples of Aero motors that are out there. So I mentioned Magnix as it was fitted in the Harbour Air and the Cessna E-Caravan. So this is an Australian company, been developing this for many years, and they are going through certification programs. So they are not far from being able to operate commercially, and they are fairly powerful machines. In this particular case, they have 2 stacked rotors, so you can see 2 sections there stacked together. So it's a common shaft and 2 rotors, and the machine is a permanent magnet synchronous configuration, with the rotor having surface magnets, and it's fairly hollow in the middle, so they've taken a lot of the mass out. It's almost like a disc rotating very near the outer casing where the stator is. And each of these sections has dual coils, so they have dual 3-phase coils, and there's 2 sections, so they have 4 3-phase coils. That gives you a fairly high level of redundancy. Now, those coils, operate in synchronism, and when they are all operational, you have full power available from that machine. And when a fault develops, all these coils are independent from each other, and the drive systems will be independent from each other, so they can decouple one of those paths and carry on operating with 3 coils at 75% power rating. This is another example from YASA, which is a UK company. Now, in this case, this motor design is an axial design. So this is, is fairly, I'll say fairly new. It's not new in that it's been around for 10, 15, maybe 20 years, but much newer than the radial flux machines that we've seen for hundreds of years. What they can do is that there's 2 configurations, but to keep it simple, you have your rotor with your magnets, and you have your set of coils establishing a magnetic field in the axial direction, along the length of the shaft, if you like, and the magnetic path is fairly short compared to the radial motor, and that makes it very efficient, and they can pack a lot more power into it in a small volume. So it is a good solution for an aerospace application, and this is the type of motor that Rolls-Royce use in their accelerator. And as I said, they can also stack multiple units along the same common shaft, and with each section you have a set of coils. So you stack multiple ones, and you start building your redundancy and your power level at the same time. This is another one from Siemens. This is standard permanent magnet motor, and another one from Danfoss. This one in particular is from a startup company in the US, but they're claiming very high power density levels, and the way they've achieved this is by using additive manufacturing techniques, where they print the coils and the stator of the machine, and that allows them to have geometries where they can pack a lot more of the materials compared to a regular wound stator. Now the electrical diagram of a dual coil rotor would look like that. So you have full galvanic isolation between two different drive units and the coils. So a fault in one of the coils or the drive system cannot propagate to the other system. And when both are operational, then they can operate at a 30-degree phase shift from each other, which has benefits on the DC side, as it makes the harmonics much lower. So a little bit on power distribution. I've been mentioning a lot that we like to operate at high voltage. So just to put that on the ground, most cars have a powertrain running at 400 volts, but in contrast, most electric aircraft will operate at 800 volts because they can achieve the lower losses in the wiring. They can use thinner gauges in the wiring and make the whole system lighter. Now, in a conventional system, you'll have a symmetric aircraft design where you have your left and your right bus, and you have DC bus ties with contactors. So you can isolate a fault in one of the sides of the aircraft, and then route power through the bus tie from the other side of the aircraft, and maintain a certain level of integrity. Now, what's happening with the multi-rotor aircraft is that they no longer need those DC bus ties because they have so much redundancy in the system. So they can fully isolate a whole powertrain from other powertrains. So you can think if you have 8 rotors in your aircraft, maybe you only need 4 fully independent powertrains, and each of the high voltage buses powers 2 propulsion units, or combinations of this. Some of the challenges with high voltage distribution are the insulation, conductor separation, connector selection, the wiring, and also the coils in machines become more difficult to manage because the insulation needs to get thicker, so you may not be able to coil as many turns around the stator teeth. Monitoring systems need to become high voltage, switch gear availability may no longer be off the shelf. They'll have to develop new contactors and so on. Now, I've talked a lot about the propulsion system, but there's also the whole electrification of the aircraft and the removal of other non-electric components. So as you will be aware, conventional aircraft rely a lot on hydraulic power to move flight surfaces and structures like the landing gear or doors. And we've seen a drive towards electrification, even in aircraft like the 787 and the 350. Now here's an example of what has been changed to electric in the Boeing 787. So you have some flight control surfaces that have been electrified. There's doors, there's landing gears, there's braking systems. This also on the 787. Now the drive for this braking system was that you have hydraulic fluid, which is flammable, close to the pads that generate a lot of heat as they engage, right? So a leak on the hydraulic lines could generate an explosion as those pads come into action. So turning into a fully electric system eliminates that problem completely. There's various pumps. Now in an electric aircraft, you may not have hydraulic pumps, but you will still need your thermal system and your environmental system. So you will need maybe liquid coolant to be pumped around your battery and your motor and inverter, and obviously all the pneumatics required for the environmental system in the cabin. Another load that's required in aircraft that fly in icing condition is to keep the wings and the leading edge of the vertical stabilizer and the wings free of ice, so that you don't lose aerodynamic performance. So in the 787, this was done with thermoelectric system, where they have heating elements along the edge of the wing, and they can circulate power to keep those wings ice free. So again, something like this could be done for the all-electric aircraft. So that brings me very close to the end of my talk. There is a lot of activity around urban air mobility and regional hybrid and all-electric aircraft, and certainly is changing the way we see aerospace and making the aerospace industry more environmentally friendly. There are challenges, and those challenges are being tackled one at a time, and I'm pretty sure that we will get there. Some of these companies like Pipistrel and Volocopter have already done by certifying their aircraft. Others will follow. Lilium and Joby are the next ones in line, but we will get there. Thank you so much for listening to me. You can follow us at Ricardo or LinkedIn, Twitter, or YouTube. And now I will welcome any questions that you may have. Thank you.
Thank you for that, Temoc. Very interesting lecture. Quite a few questions coming in. So these are in, hang on, I better do them in order, else I'll get them wrong. One from Peter Chan. So how does the efficiency of the smaller motors and propeller compare with fewer larger motors and associated propellers and fans?
That's a good point. They're not as efficient. The smaller motors, could be running as low as 85–90% efficient, compared to the larger machines that we see. The several hundreds of kilowatts machines that will be running at 95–96%. So yes, from an efficiency point of view, it's better to have larger machines than small ones.
Okay, fair enough. I think on one of your early slides, you mentioned the Airbus, one of the Airbus prototypes. Do you know if they are going to carry on work with the E-Fan-X, or whether that has died a complete death?
It's died a complete death, unfortunately. But Rolls-Royce took on all the electric powertrain with them. So as you may recall, E-Fan-X was a venture between Airbus and Rolls, and Airbus were going to provide the aircraft, and Rolls were developing the electric powertrain for one of the engines, and then they were going to fly the demonstrator with 3 conventional engines and 1 fully electric engine, and there was going to be a turbo generator generating 2 megawatts of electric power for that one electric machine. So they binned the project. It is dead, but Rolls took on all of that learning back to them, and Rolls are very, very active in developing electric powertrains across a number of platforms, from the urban air mobility to the regionals to the larger aircraft. So yes, I think Rolls have a strategy to modernize. Obviously Rolls is a flagship company for the UK. We are very proud of them, but they need to keep abreast of technology and what's happening with global politics and environmental politics, and I think that's what they are doing at the moment.
Okay, a question from Mike B, which is regarding regulation. Are there specific regulations for electric propulsion, and are the regulators keeping up with the use of large batteries, hydrogen fuel cells, etc.?
Yeah, just about. I've asked that question in so many forums, and they're always cagey about it. The way the regulators work is that if you have a platform and you're developing new technologies, you need to engage with them, so that you develop the regulations with them. Ultimately, all our goals are to make aircraft safe for passengers to travel. But there is a precedent now with Pipistrel and volocopter already certified. For the air taxis, they have, EASA has developed the spatial conditions for eVTOL, which is now out there. So again, you know, there is guidance material out there. For the larger aircraft, they fall under Part 23 for aircraft up to 19 passengers. And yes, it does not cover specifically, you know, large capacity battery packs, but the general guidance around battery management applies. And there's, of course, the RTCA DO311 regulation of means of compliance with high energy batteries. So yes, there is material out there that we, you know, all these companies can start following and developing their systems.
Okay. I've got a question here, which the answer is no, but it goes, are you going to mention the Electric Airlander 10? You haven't done. Do you know anything about it? So I'll add an extra question on the end of it.
Can you repeat the name?
It's the hybrid air vehicle, the Airlander.
The Airlander.
Looking at putting a hybrid engine on that.
Yeah, I mean, I'm not too fully familiar, but yeah, this is an airship, isn't it?
Yeah.
It's not the conventional electric propulsion aircraft that we you know, are particularly keen on. So yeah, I mean, the short answer is I'm not looking into it. I've heard about it. I'm sure there will be a market for it. You know, I'm not the type of person that shuts doors on business ventures. So yeah.
Okay. Question from Pavan. Can we carry over the learning on energy management from the automobile industry to aviation? And is anything happening in that area? I guess he's talking about like energy recovery systems. And
yes. Well, there's multiple things, but yeah, battery management systems for vehicles can be translated to aerospace with a caveat that, you know, aerospace needs high integrity systems and redundancy. So there may be a need for two battery packs instead of just one, or there may be rerouting of battery strings into different high voltage nodes. In terms of the energy recovery, totally yes. You know, as the aircraft, particularly, you know, conventional landing aircraft, as they slow down, they can run the machines as regenerative braking and recharge the batteries as they slow down. There's not much energy in there, but it is possible, and the machine drives, the power electronics that drive them, are perfectly capable for running in regenerative mode. So yes, completely. Okay.
Question to do with I think the weight, based on the weight of the batteries, which is, should the criteria not consider the maximum landing weight instead of the maximum takeoff weight, which I think is what your chart showed.
Yeah. I mean, there were. There's a few details around that table. So, for example, conventional fuel aircraft get lighter the further they travel into their mission, right? Because they burn the fuel, and as a result, the aircraft becomes lighter, and that allows them to travel even further. With battery-powered aircraft, that does not happen, right? The weight you take off with is the weight you land with, plus minus a few electrons. But yeah, in general, you know, the landing gear system and the structure of the aeroplane have to be designed to land with that maximum weight, which is not always the case with conventional aircraft, where they can relax the landing weights, and even when they have to do a turnaround maneuver, they can jettison fuel to make it lighter so that they land within the specified landing weight. So that's not the case with electric aircraft. They will have to design the structure and the landing gear for the maximum weight.
Okay, thank you for that. A question from Harry Firth. How much can hybrid aircraft reduce the net carbon emissions for a whole flight and not just the pollution around airports?
So if we go with a fully green hydrogen economy, that is it. Yeah, we've eliminated emissions, and that's full stop. That's a big if, right? That is changing our entire energy grid. Hopefully we'll get there one day. It will not be overnight. It will take 50, 60, maybe 100 years. Now, there's another approach with synthetic fuels, which again use a lot of energy, but allows conventional aircraft to carry on flying. And the idea around the synthetic fuels is that they can use renewable energy renewable energy and something around carbon sequestration. I can't remember exactly, but it ends up being carbon neutral. And yes, when they burn the fuel again, it generates CO2, but then they trap that CO2 somehow. I can't remember exactly how it works. But the idea with synthetic fuels is that the airline industry can become carbon neutral.
Okay. In the slides you mentioned superconductor materials were used. What sort of systems and designs are being developed with this technology?
Yes, so here is the twist, right? So once we have liquid hydrogen on board aircraft, well, like liquid hydrogen is cryogenic. So you could then cryogenically cool your distribution network and then your power electronics and your machine, which has enormous benefits on power density and machine design, right? Just to give you an example, that a wire the thickness of a hair can transport 100 amps, right? Whereas now you'll need maybe a wire that is 10 millimeters in diameter. So again, yes, of course you'll need your cooling jackets around your cryogenic cooling, but overall it will bring the system weight down and the efficiency up. So yes, potentially that could be a big disruptive technology for future aerospace systems. Okay.
I'm not sure I understand this next question, so I'll give it to you as it's said, and then we'll see if we can work it out. Will electric aircraft allow them to use Heathrow's third runway for longer? So I'm not sure whether he's talking about the amount of time during the day they can use it, rather than the lifetime of the runway. So I think it's the former.
Yeah.
So I guess it's more associated with noise and pollution.
Yeah, I haven't given it much thought about the current Heathrow layout. I think if electrical aircraft start flying from Heathrow, they really need to change the logistics around it, because Heathrow is one of the most busy airport in the world, and they have huge penalties for aircraft parking at the gate or elsewhere for long periods of time. So they want those aircraft, landing, disembarking, boarding, and taking off as soon as possible. Otherwise, they get penalized. So if this conversion to electric aircraft happens, well, they will have to think about where are they going to fit these electric aircraft and for how long, and whether they're going to do battery swaps or fast charging, and that takes time. So I don't know if it's specific to the third runway, but the whole aircraft operations needs to be rethought, right, and morphed into a future electric aircraft operations. And there will still be need for those long-haul conventional aircraft, but yeah, maybe they'll repurpose one of the landing strips for electric aircraft, and they'll keep the others for conventional aircraft. I don't know.
Question from Don B. How difficult would it be to suppress the electrical interference from the power system to like the avionics and navigation equipment?
Yeah, so it is a requirement. If we design sophisticated electronic systems, they have to meet very stringent electromagnetic interference levels. And the way we do that is, for example, in power electronics drives, is there's a trend to switch higher frequencies, especially with the new semiconductor devices, wide bandgap semiconductor devices like silicon carbide, gallium nitride. And that allows us to fit filters that more easily filter those switching events at high frequency. And then there's techniques like spread spectrum of the switching frequencies, which bring the overall peak levels down, and they distribute the energy across a wider band of frequencies. But essentially that then allows us to have smaller filters that completely get rid of any noise coming out of those enclosures of the motor and the motor drives.
Okay, thank you. Question from Dave H. How reliable are these early electric designs compared with jet and piston engines?
They are a lot more reliable because there's fewer moving parts. These machines, there is one moving part. That's it. And the electronics, there's no moving parts. Then your cooling system may have, it will have a pump to pump the fluid around. Again, just one moving part. So overall, there's a lot less parts than in a conventional engine.
Okay. In current aircraft, the cockpit cabin conditioning and onboard oxygen is generated from the superheated air coming out the jet engines. How would this work on a fully electric aircraft?
Yeah, I mean that's one of the headaches, isn't it? You get bleed air from your engines, you pump it in, and that you use that to pressurize the cabin and temperature control and whatnot. You don't have that, and you do not want that in an electric aircraft. You want your propeller or ducted fan and machine working as efficiently as possible. So what that means is you will have to have ducted vents in other parts of the aircraft, and then have compressors in to pressurize your cabin.
Okay. Question from Sunil, which is, can you reduce the battery size by using solar panels while the aircraft is at high altitude?
You can. The surface area of the aeroplane is not that large, so even if you were to fully populate your top surface with solar cells, it wouldn't make a significant impact on the energy that the aeroplane requires to get you somewhere else. Now, it may make a difference if it's just parking, somewhere, especially for the smaller GA aircraft. If you land in a farm field somewhere and you leave it there for the whole day, it may give you a sufficient level of charge.
Okay. A question from Ed. You talked about redundancy quite a lot, but are there any specific reliability issues to address that might compromise the overall integrity of the system?
And not really. I mean, the redundancy comes in to meet your safety objectives, right? So if you think of, let's think of a twin propeller aircraft. At the moment, each engine and propeller has to be designed for a 10 to the minus 7 probability of failure, right? And combined, it gives you quite a small probability of both engines failing. And that's the premise behind, twin jets and twin propeller planes. So if you replace that with your electric counterparts, the probability is still the same, right? If you only have 2 propellers and 2 electric machines, they still have to meet 10 to the minus 7. And if one goes, you're still able to fly with the remaining aircraft with a lot of yaw in your aircraft and steering to do or whatnot. Now the difference is now that in electric machines we are able to have dual actuation because of dual coils, and we also have stacked rotors, which again gives us a lot of redundancy. So instead of having to design each section to meet 10 to the minus 7, we can now design to meet 10 to the minus 5, which is less stringent. And if the aircraft is designed in a way that it can fly with 100% power from one engine and 75% power from the other engine, and still complete its mission, for example, maybe at a longer time, then that is a good result, and you've lowered the design target for reliability of one section. So you made the engineering task easier.
Thank you. Fair enough. Question on, I guess, here on the flammability and smoke risks of electrical designs. Is there any specific regulation or things you can do that help slow the flame propagation or diminish smoke and toxicity issues?
I mean, the regulations are there. The DO 311 provides a means of compliance for battery pack designs. And essentially what they say is that you have to contain the smoke, and if you're not able to contain the smoke, then it has to be vented to the exterior of the aeroplane. So what that means is that the pack will have to be placed in an aircraft zone that has access to venting, and it has to be managed in a way, through pressure relief valves, or in a way that any smoke generating a high pressure in the pack then is vented through to the external of the aeroplane, but it must not propagate to adjacent cells. So that pack remains operational for the remainder of the flight, and it allows the passengers to evacuate in a safe manner. And of course, at that point, then it can be serviced and repaired.
Okay. Anonymous question here. How many cycles can a lithium-ion battery last compared with the air lithium battery? And how long would it be before that battery couldn't be obviously recycled, reused?
Yeah, it's about 1,000 cycles. So lithium-air, as I say, the prototypes it built only got them to about 10. So they still have a long way to go.
Yeah, otherwise it's going to be very expensive, isn't it? A question from Pete D. Are there any security concerns with an all-electric propulsion system? Does it open any new attack vectors? So I guess we're talking about more terrorism and
that's right. Cyber security has been a big hot topic in the last 5 years, and in the last program I worked for Mitsubishi, it was a hot topic, and we had to demonstrate how our systems were tolerant or prevented cyber attacks. So it is a real concern, not just for all electric aircraft, but in general, aircraft in general, because what's happening is that these heavily instrumented aircraft and heavily optimized aircraft are constantly relaying data to hubs. So I'll give you an example. Rolls-Royce monitors their new line of engines in all the fleet, right? So that they can use that data to optimize the design, optimize throttle responses and the amount of fuel that they burn, optimize emissions and so on. But they can also control parameters into it. And that's where cyber becomes a real threat, right? Because if you have a way to sending control data to an aircraft, then of course that can be targeted by cyber terrorists, and they could control it in a way that that aircraft becomes a danger to us. But any such system that allows an access door to data then has to go through a number of firewalls and encryption and etc. to make it secure. But yes, it is a real threat. But I think the approach to counter it is there.
Okay, and we'll call this the final question because we're getting on a bit now. From Mike, is there consolidation in the industry going on? I believe Rolls-Royce recently bought Siemens Aero engines.
That's right. I mean, Siemens were one of the partners in that EFAN X job, and then Siemens pulled out and Rolls took that on. Yes, there's consolidations and also failure to consolidate. At some point last year, Boeing were going to purchase a branch of Embraer, and that fell through. And we've seen, I think it was Airbus who purchased a branch of Bombardier. Mitsubishi also bought a part of Bombardier. So yes, there's a lot of activity at the moment because of how the industry is suffering, and there'll be fewer big players out of this. But as I said earlier, there will be a lot more newer players in this nascent market of urban air mobility.
Okay. Final question for you to speculate a bit on. So when do you think we'll see the first transatlantic all-electric flight?
Oh, brilliant. I love to see it before I die. I mean, it's a long-haul route, right? It's a 3,000-mile London to New York City. So we are some time off. I think the roadmap for this lithium-air technology to become viable commercially is 10 to 15 years. So where are we now? 2035, we might see a demonstrator flight that is all electric across the ocean.
Okay. Right. Well, I'd like to thank you for what was an extremely interesting presentation. We do give our guests a token of our thanks, which is the Cody Flyer paperweight, and we'll make sure we get one of those to you. So I'll get your address off one of the guys later. And yeah, thank you again. It's been a very interesting lecture, and I'm sure we'll come back and revisit in a year or so's time, or a couple of years' time, and see how we're actually getting on that roadmap.
Thank you so much for having me, and thank you for all the participants to listening to me, and hopefully it was of use and time well spent. Thank you.
Thank you very much.
Thank you, and good night.
Good night.